So we're on page 509 in the Absolute Value Workbook for Math 20 and looking at how to solve a system of quadratic equations. So essentially we're looking at a system of equations having two quadratics. Both quadratics in this case are in the form ax squared plus bx plus c. So again, remembering if we're trying to determine the solution to the system, the solution for any system represents points of intersection or points of intersection. If you were to graph, certainly algebraically, then we are looking for values of x and y that satisfy both equations. So algebraically, our two methods that we can choose from are substitution as well as elimination. In this particular case, substitution works out really nicely because in both cases y is isolated, so you have y equals this, y equals that, and therefore they must equal each other. So we can then say that 6x squared plus 7x minus 4 must equal 2x squared minus x plus 1, and so since that in itself becomes a single quadratic, and then to solve a quadratic we know that we want to set one side to 0, so we'll make sense to move everything in this case to the left side, so we get positive x squared coefficient, so we'll subtract 2x squared from both sides, add x to both sides, and subtract 1 or add negative 1, same thing, to both sides. So then that gives us 4x squared plus 8x minus 5 equal to 0. And to solve that quadratic we have a couple of options. So option 1, we can dive right into quadratic formula, or we can attempt to factor it first and see if we can get some rational values. So if we factor that, let's take a look. If we do 2x and 2x, and I know that we've got to have a 5 and a 1, and so positive 10 minus 2 will give me my positive 8x. So we factor that, we'll double check of course, because we want to make sure, because if I'm not factoring correctly, then the trickle down, everything else is not going to work out. So I've checked my factoring. That is in fact 4x squared plus 8x minus 5 equal to 0. So that means that either negative 2x minus 1 equals 0, or 2x plus 5 must equal 0. So we've got these two little mini equations. Add 1 to both sides, so 2x is equal to 1. Therefore, x is either equal to 1/2, or on the other side we subtract 5. So 2x equals negative 5, divide by 2. So x equals negative 5/2. So we've got those two options for x, but we're not done, because remembering our solution, we're looking for that point of intersection, or values for x and y. So we need to figure out what the corresponding y values are for each, and so I can decide which equation I'm going to substitute into. So I'll just number them here for you to see. So if equation 2, the numbers seem to be smaller, so might as well use that then. So if x is equal to 1/2, then we would have y is then equal to 2 times 1/2 squared minus 1/2 plus 1. And working that out, we've got 2 and 1/2 squared is 1/4. Minus 1/2 plus 1, so 2 times 1/4 is 1/2, or 2/4, so 1/2 minus 1/2 is simply 0 plus 1, so that is going to be 1. That is our corresponding y value. So let's take a look for the other one then. If x is equal to negative 5/2, then the y will equal 2 times negative 5/2 squared minus negative 5/2 and then plus 1, so squaring first, so 2 times 25 over 4, and then plus 5 halves, plus 1, and we can simplify this, so 2 over 4 is the same as 1 over 2, so I've got 25 halves plus 5 halves is going to give me 30 halves. 30 halves is also known as 15, plus 1 will then give me 16, so y would be then equal to 16. So just to be clear then, our solution is, or are, because there's 2 points, we want to be clear, we've got x equals 1/2 and y equals 1, as well as x equal to negative 5 halves, and corresponding is y equals 16. You could also write those as 2 ordered pairs as well. Okay, so sketching the equations on the grid and using a graphing technique to determine the solution to the system, state an appropriate window. So that implies, of course, then that we'll use our graphing calculator. So going through that then, so take out your graphing calculator and we'll enter in both equations. So I've got y1 equals equation 1, y2 equals equation 2, and we'll just go ahead and graph on your standard window. And if you look at that, then we can see there's that first intersection, which appears to be x equals 1/2 and y equals 1. We wouldn't know that for sure just by looking at the graph. The other graph, of course, since the y max in our standard zoom window is just a maximum of 10, so we can't see that other intersection, which is why we're going to need to adjust our window setting. So the window setting, if we wanted to, certainly we can carve off a little bit on the x min and y min if we wanted to, but the most important thing is for us to be able to see that y maximum. So let's go to our window and we'll adjust our y max. And so since we know that correct answer is 16, I definitely want to go higher than 16, so 20 would certainly work. And so if we graph that now, we can see both intersection points. So we can just sketch both of those graphs onto our grid then. So for one, we're looking at this guy right here, and then the other one might be something like this then. Like that, and there are our 2 points. Okay, so it's definitely not perfect by any means, but we're just looking at a sketch at this point. So my appropriate window, then I kept my x is the same, so my x min was -10, x max was 10, and it counted up by ones, and my y values for my window, my y min was -10. I increased my y max to 20, and I kept the scale at 1, meaning we're counting up by ones in this particular case then. Okay, and so again, using our calculator, just to remind you of finding those solutions. So since there's 2 solutions, when we ask it to say second trace or calculate, we're looking at the intersection, so the 5th option. So you can move the cursor down to the 5th, or you can just hit 5, hit enter, and so it's asking you the first curve. So pick which one you want to do first. So if we want the one on the right first, as long as the cursor is going to be closer, it doesn't have to be right on the intersection, it has to be closer to that intersection than it is to the other one, and certainly it is. So we'll hit enter, and then now you can see that it says second curve and it's switched to the second equation, or the red one. and we're again closer to that intersection than the other one that is at negative 5 halves and 16. So we'll hit enter. It says yes, absolutely, and there it is. X is 1/2 or 0.55 tenths, and y is equal to 1. So then if we want to find our second intersection point, our second solution, so once again intersect, and now I need to move my cursor over so that it is definitely closer to that other intersection. So I've got that there, hit enter, and you can see that it automatically adapts with the second graph then. So hit enter, take a guess, of course, and there it is. X is equal to negative 2.5, also known as negative 5 halves, and y 16. Excellent. So the verification we're looking for is an algebraic verification. So with this, we need to verify that both solutions work for both equations, and therefore that will take 4 verifications then. So for 4 left side, right side checks essentially. So we're going to verify x equals 1/2 and y equals 1 first in the first equation. So in the first equation, the left side was equal to y, of course, so that's just 1, and the right side was equal to 6 times x squared, so 6 times 1/2 squared, plus 7x, or 7 times 1/2 minus 4. And if we work that out, we've got 6 times 1/4. So because 1/2 squared is 1/4, so 6/4 plus 7/2 minus 4. So 6/4 is also known as 3/2. 3/2 plus 7/2 is 10/2. Minus 10/2 is also known as 5. Minus 4 is of course equal to 1. So that one works, and we'll move on. So we want to verify this in the second equation as well. So in our second equation, the left side was equal to y again, which is just 1. The right side was equal to 2 times x squared, or 2 times 1/2 squared, minus x, or minus 1/2, plus 1. And so then again, 1/2 squared is 1/4. 2 times 1/4 is 1/2. Minus 1/2 is 0. Plus 1 is just 1. So left side equals right side. So far so good. So now let's take a look at verifying the other solution. So based on the first verification that we did, though that point x equals 1/2, y equals 1 worked in both equations, so that confirms that that is one of our solutions. So we want to verify x equals negative 5 halves and y equals 16 also works in both equations. So in the first equation, the left side was just y, which is of course 16. The right side was equal to 6 times x squared, so 6 times negative 5 halves squared, plus 7x, or plus 7 times negative 5 halves, and minus 4. So then if we square that, we've got 6 times 25 over 4 plus negative, so we can just go with minus then, minus 35 halves and minus 4, and so 6 over 4 is the same as 3 over 2. So then we've got 75 halves minus 35 halves is going to be 40 halves. So 40 halves minus 4, well, 40 halves is also known as 20, and 20 minus 4 is 16. So left side equals right side there. So we'll check in the second equation then, and left side was again y, so y is 16. The right side for that one is 2 times x squared, so 2 times negative 5 halves squared, minus x, so minus negative 5 halves, so I'll just write plus 5 halves, then plus 1. So squaring negative 5 halves is, of course, 25 quarters. So 2 times 25 quarters plus 5 halves, oops, plus 1, and so 2 over 4 is the same as 1 half. So we've got 25 halves plus 5 halves is 30 halves, also known as 15 plus 1, which is 16. So left side equals right side. So that does in fact confirm that that solution works as well in both equations. Excellent. So that's it for the examples that we have. So please let me know if you have any questions.